Welcome to today's lecture. Today we are continuing our amplifier design lectures. So, today we will see another class of amplifier which are broadband. We have seen that if we do conjugate matching, that match and also S parameters of any transistor, they are true for any particular frequency, but many times we know that since our baseband signal is a band of signal, it is not a spot frequency. So, we try to design amplifiers for a bit broader band, and with today's technology etc., more and more new applications are coming which are demanding much broadband amplifiers, because the baseband signal is also going large, and also in RF the bandwidth etc., to have high data rate systems, the bandwidth is increasing. So, RF signal also should be having quite large bandwidth. So, the onus on amplifier designer is he should know how to design broadband amplifier. Now, broadband problem is, you see that microwave transistors are typically not designed with 50 ohm level, but source and loads, these two sides typically are 50 ohm, that is an electronic industry standard. Generally in lower frequency that was 100 ohm, but in nowadays the industry standard is 50 ohm. So, we should have this, ultimately any amplifier should be designed for 50 ohm, but unfortunately if we look at the S21 parameter of the transistor itself, device itself, that has a frequency response which decreases with frequency. Typically it is a fall off of 6 dB per octave. So, as we go higher and higher in frequency, S21 decreases. So, that problem now we will have to tackle when we attempt a broadband amplifier design. So, there are various approaches. I am just letting you know what are the typical approaches. The first approach is design with conjugate matching at a particular frequency, typically that is center frequency of the band in which you are trying to design the amplifier. You know, center frequency can be the amplitude mean, arithmetic mean, or it may be geometric mean, or it may be if a band is properly defined, the center of that band. Now, then what you do, you know that at other frequencies you have designed for a center frequency, at other frequencies either lower or higher than the design frequency, the S21 will fall. You have a matching network which will compensate for that change in S21. But obviously, here due to this matching network, the input and output mismatch at frequencies other than design frequency will come. So, you will have an input output mismatch, and that will also have some, you will lose some power in the mismatch things. So, this is one of the design. So, by knowing conjugate matching and impedance matching, you can attempt this. People many times do this, but let us see another approach. Another approach is, you instead of conjugate matching, you design with different gains at different frequencies, and for that you apply whatever we have discussed in specified gain design concept, that draw the specified gain or any constant gain circle at that frequency and try to have the matching circuits for that. And so, if you want to do it for over a band, basically over all possible frequencies you cannot do. So, you select typical various frequencies in that band, and there you do that design, and finally, with trial and error have some balance, but some trial and error effort is needed, but people also do it. We will also see an example of this in the examples. Then approach 3, you can also have resistive matching network to tackle S21 frequency response. It is good because you see that in output and input matching, as the resistor has a flat frequency response, you will have more or less a frequency response good, but obviously since you are using resistive element, you will have some loss in gain. Also due to resistance, you will add more noise. So, some noise figure will also shoot up, Now, this is also another approach. We also have seen many times that in resistive loading we have stabilized transistors. Similarly, here we are doing broadband with resistive matching network. Fourth alternative, here negative feedback you can use. You know, any negative feedback that will be make your input and output matching better, because any negative feedback that flattens the frequency response. So, S21's frequency response, that with feedback that will be a bit flattened. So, you will get flatter gain versus frequency response, better stability. Obviously, negative feedback makes the any amplifier circuit stable, but here also you will get, because of negative feedback, your gain as well as noise performance will degrade. But this is a new very elegant concept. This is the fifth approach. Here you can use a balanced amplifier, and the beauty of this is, apart from all other previous four, here no input and output matching needed. Obviously, there will be mismatches, but we will see that we can avoid that. There are no input output matching circuit needed. We can have balanced amplifier, and we can get typically an octave of bandwidth. That means, if suppose I have a design frequency of 5 gigahertz, typically I can say that I will also have a bandwidth of 5 gigahertz. That means, I can have from 2.5 gigahertz to 7.5 gigahertz. Typically 5 gigahertz bandwidth is the huge bandwidth. Generally we require 500 megahertz, 1 gigahertz bandwidth, but nowadays applications are coming, particularly ultra wideband systems are coming, for which this type of bandwidth will be needed one day. Balanced amplifier will be able to do that. In balanced amplifier, we will see in details. This balanced amplifier, it uses two amplifiers instead of, that means two active devices. Instead of one transistor, we have two transistors, and so obviously the DC power requirement is twice. That means, you know, DC power actually it uses for biasing. So, that bias DC power is not of any value for wireless transmission. So, there you are wasting some power, and also though you are using two devices, two transistor devices, the gain should have been more, but actually gain is of one amplifier only, that we will show. So, these are disadvantages, etc., but still it is for broadbanding, it is a very good choice. Now, before going here, let us see example of a broadband design from the specified gain design concept. That means, as I said in alternative 2, I think this one, that applied specified gain design concept to achieve broadband specification, design with different gains at different frequencies. This example we will see now, that broadband design first, then I will go to balanced amplifier. Suppose the S parameters of a BJT are given in 300 megahertz, this is the S parameter. You see, we are assuming unilateral, that is why S12 is not specified. Similarly, 450 megahertz and 700. Now, it is asked that design an amplifier with a transducer power gain of 10 dB from 300 to 700. So, let us see. Now, first let us see whether it is feasible or not. So, we see S21 square already given at different values. So, if we calculate, it turns out that at 300 megahertz I have 13 dB, at 450 megahertz I have 10 dB, and at 700 megahertz 6 dB. That means, I have this, I am supposed to get 10 dB gain. In 300 megahertz lower frequency I have 3 dB extra. So, I should have a matching network which should give me basically an attenuation of 3 dB. Similarly, at 450 megahertz it is okay, and at 6 dB we should squeeze from matching networks input and output both together another 4 dB. So, matching networks needs to provide attenuation of 3 dB at 300 megahertz, gain of 0 dB at 450 megahertz and gain of 4 dB at 700 megahertz. Now, is it possible? Let us see. Now, we know that how much gain I can get from the source side, that is in the lecture on specified gain etc. we have seen that maximum gain I can get from the input side is given by this. So, that from the S11 tabulated values I can see that I can squeeze out from the input side 0.409 or this and this. Little advantage you see, not much I am getting from input matching, but output side let us see. So, from the output side I can get a gain of 5.6 dB over the band. So, output matching can give me that 4 dB that I require at 700 megahertz. So, it is feasible. If this was outside the range of this, suppose this value if I did not get 5.6, but suppose I got it 2 dB, then I said that no, with this transistor I cannot have that broadband thing, but here we are getting. So, let us proceed hence it is feasible. Now, design procedure: plot constant gain circles, GL is equal to minus 3 dB at 300 megahertz. So, we are doing it for output side, load side, because in input side we can have anything and that will give us something. So, GL I require minus 3 dB at 300, 0 dB at 450, 4 dB at 700. We have plotted these circles 700 megahertz, these are the circles. Now, matching network must transform the 50 ohm load to some point on minus 3 dB gain circle at 300 megahertz, some point on 0 dB gain circle at 450 and some point on 4 dB gain circle at 700 megahertz. Let us see, since it is megahertz, we need not go for distributed matching, we can have L matching. You can also go for distributed, you know how to do that. Let us, in this example we have chosen an, so there will be input matching, output matching, lumped element matching. So, many designs are possible. One design is like this. So, constant gain circle, these are the calculations you can note down. Then you know that here actually I have the load. Now, from this S22 value, that means this is the towel, I need to now transform and then go to that 1 plus GB circle at 300 megahertz, at 450 megahertz I will hit it here, at 700 megahertz I will hit it here, and then accordingly I will choose L1 and L2. So, choice of L1 at 300 megahertz, let us say that this is giving that choice, this is the Smith chart part. So, 300 megahertz we are from the load, I am moving here, first I am converting and then moving here. So, I am hitting it here, L1 transforms 50 ohm to this, L2 takes it to load point. So, shunt inductor will be L1, susceptance decreases it. So, it is decided from low frequency 3 megahertz 300 megahertz plot. Which side I am going? So, from trial and error we can do this. Now, let us see a balanced amplifier design. Now, what is a balanced amplifier? You see here I have one amplifier here, let me call it amplifier A, this is amplifier B. Now, so there are two amplifiers we are using. Generally, we will see that we try to make these two from the same lot, so that I have identical things. Now, here you see this dashed one, there is a coupler here, basically a 3 dB hybrid. Already in our basic building blocks NPTEL lecture, we have seen what is a 3 dB hybrid is. 3 dB hybrid can be acted as a summer, as an subtractor, etc. Also, we have seen a lot of applications of 3 dB. So, we are using a coupler here, 3 dB coupler here. before the amplifier, also after the amplifier. The input we are giving here, the fourth port of the coupler we are terminating by a match load. Similarly, these output couplers, the port 3 we are doing it terminating with match load, here we are putting it with this. Now, this is the diagram, this is directional coupler 90-degree hybrid. I have two transistors, their gain is GA GB, and I am applying V1 plus in the input to the input coupler port. Obviously, the V1 minus goes out here, but you know that I will get signals both here and here. This is the through port, this is the coupled port. So, I will get signals, and then again through this amplifier, this whatever signal is coming in this through port, that will go here. Similarly, from here whatever is coming, that will come here. Then again I am putting it to the coupler. So, this signal will get coupled here, this one will go here. So, this one I will get it here. Similarly, from here whatever reflection is coming, that will come here, and again it will come here. So, I will get some V2 minus here. Now, let us quantitatively see what is VA1. We know that this is voltage. So, I will have 1 by root 2. This is from your hybrid thing, you refresh, that I will get in the through port, I will get VA1 is equal to 1 by 3. This is 3 dB, that is why I am getting this 1 by root 2 in the voltage. In power it is half. So, V1 plus. Then VB1 plus, this also is how much? This V1, then due to 90-degree hybrid I will get a minus j, and then V1 plus. Then V2 minus, what is V2 minus? It is, we know that this VA2, there will be a 90-degree change here, and whatever this, that is same 1 by root 2 here. So, now then VA1 plus, what will be this VA1 plus 1 by root 2 V1, VB1 is this. So, you see that if I put it, V2 minus is what? Minus j this plus 1 by root 2 this. Already remember this, put those values of A2, and so A2 you can put it here, and finally you see that this is GA plus GB. So, V2 minus I have in terms of V1 plus, immediately I can write the S21 parameter. S21 of this whole thing will be V2 minus by V1 plus. When V2 plus is 0, we have made V2 plus 0, because you see we have match terminated it. So, this value is GA plus GB. So, you see S21 is this. Now, if we have identical transistors, let us assume GA plus GB. So, it is simply S21 is GA by 2 with a phase change of 90 degree. So, overall gain of balanced amplifier is average of individual amplifier gain. So, that is why we said that though we have two amplifiers, but actually we are getting gain of 1. But where is the beauty? Again you see that V1 minus, if we see that how much we are reflecting, V1 minus is 1 by root 2, VA1 minus, VA1 minus means, and then VB1 minus, VB1 what is being reflected here, that is coming here with a 90 degree phase shift, that is why minus j by root 2. Then you know that VA1 minus, VA1 minus is nothing but gamma A into VA1 plus, and VB1 minus is nothing but gamma B into VB1 plus. So, if you put that, then we get V1 minus is equal to V1 plus into this is nothing but gamma A and gamma B you can take common. So, it is gamma N minus gamma B. If these two are identical, then V1 minus is equal to 0. So, you see that though there are reflected signal from individual one, but with this balanced one I am getting V1 minus by V1 plus is this. So, what will be my S11? S11 will be gamma A minus gamma B by 2. So, S11 is half gamma A minus gamma B. Now, if we have balance, if gamma A and gamma B are same, we are getting no reflection. So, no need of matching circuit etc., it is always matched here. For identical amplifier, S11 is 0, S21 is GA, we have already seen that previously. So, no need of impedance matching. It is an elegant concept, this balanced amplifier. Only thing is you are required to have 2 transistors for this. Now, issues with balanced amplifier. If one amplifier fails, what will happen? Nothing will happen, your overall gain will drop. You see that if suppose amplifier B fails, so what you get is half of this in S21, that means your in dB scale you are getting a in voltage gain that is falling by 6 dB. Overall gain drops by 6 dB. Some power also we are losing in couplers, because those couplers are we are putting passive devices. We know coupler has some loss. So, some power is lost in coupler. Also noise figure of the overall thing will be Fa plus Fb by 2. So, noise figure also will change if the two noise performance of 2 transistors are never similar. So, there will be some noise increase also. Now, bandwidth of balanced amplifier, you see that at every frequency this is true, but the couplers they have a bandwidth. So, basically balanced amplifiers bandwidth will be limited by the couplers bandwidth. Now, couplers typically have 1 octave of bandwidth, that is why we are saying that balanced amplifier can do broadband design, broadband amplification for 1 active bandwidth. If you can improve coupler bandwidth, you can get more bandwidth, because conceptually balanced amplifier at all possible frequencies it will have the same thing, in which it has gain. Obviously, the amplifier needs to have a gain circuit, that means it is much before its maximum usable frequency where gain becomes 1. So, it is much less than that. So, once that, then any frequency you can have this gain thing. Now, advantage is output power twice of individual amplifier power, as you have already seen before, that output power is, you see that V2 minus I am getting some from here, some from here. So, obviously, the output power is twice. Now, also you have seen that redundancy built in, I degrade my performance if one fails, but the whole thing is usable because still amplification goes on. Easy to cascade also, because you have couplers on both sides. So, you have good isolations, we know directional couplers have good isolations. So, as balanced amplifier isolated by coupler both in input and output, you get good cascading property also. Now, disadvantage, as I said, that 2 amplifier, but gain is of single stage, wastage of DC power, size also is larger because couplers are passive things. So, they becomes bulky. Completes the broadband amplifier design part. So, you see that with balanced amplifier you can have, if you can afford the directional coupler thing. So, here also this we did not say when we discussed directional couplers. This is another example where directional coupler is changing the whole ball game and making that the whole amplifier is matched for all frequencies, though internally it is not matched, but with the balance thing finally the overall S11, the overall reflection that you are getting, that is becoming almost very low. So, also gain wise you are not losing much, you are not gaining much, but you are also not losing much, you are keeping that gain. So, it is a good design for broadband amplification. Thank you.